Okay, so today we're going to talk about probability part 3. So last time we talked about how to calculate the probability of A and B, A or B, and the complement of an event. Okay, so as a quick review, let's just talk about how would we visualize these events in a sort of like a Venn diagram formation like this. So we're not calculating probabilities right now, we just want to identify what those events are. So first of all, we've got a sample space S here. S contains the numbers 1 through 8. And let's suppose these are outcomes of some sort of game. So player A wins if the numbers 1 through 5 come up. Player B wins if the even numbers 2, 4, 6, and 8 come up. Okay, so A's values, or the outcomes which only A wins, would be 1, 3, and 5. The outcomes that would have only B win are 6 and 8. And the outcomes that they sort of both share, right, this would cause either of them to win, are 2 and 4. So this here is going to be their intersection that we call A and B. And also want to note that there's another event in our sample space that hasn't been labeled here yet, and that's 7. So 7 doesn't fall into either A or B, so that's going to be out here on its own. So this entire rectangle represents the whole sample space. And then each circle A and B represents the outcomes under which A or B would win. All right. Let's see the next example. Now we're going to consider A or B, which is also known as the union. So we've got the same values labeled here. And you can see I've already kind of shaded in blue what counts as, or what A or B sort of consists of. So that's the entire circle of A, that's the entire circle of B, including their intersection. So if we're to list the outcomes out, we would just list out 1, 2, 3, 4, 5, 6, and 8. So every number, but that's 7. So we're still not including that 7. Okay, so this was known as A or B. So let's see what's next. Now we have the complement. So it's written with, so A complement is written with this sort of C over here in superscript, sort of looks like an exponent. So to figure out the complement, the best thing to do is first figure out what that original event was. In this case, A is just going to be that entire first circle. A complement is going to be everything outside of that circle. So that's what's here shaded in pink. So it's everything outside of that circle. So that's going to count for 6, 7, and 8. So these are going to be the events or outcomes which do not fall in A, or these are A complement. Okay, so now we've got a more compound or sort of complicated set here that we're going to consider. So this is the complement of A and B, also known as the complement of the intersection. So in this case, we start off the same way. First, you're going to start off by identifying what your intersection is. So that's 2 and 4. The complement is going to be everything outside of that. So everything here in pink. So it's going to be the values 1, 3, 5, 6, 7, and 8. So essentially everything except for 2 and 4. The other way you might say this is not A and B. Okay. And the final combination we're going to consider is the complement complement of A union B. So A union B is going to be what we see here in blue. It's 1, 3, 5, 2, 4, and 6, 8. The complement of that is just everything outside of the circle. So it's just this empty space out here. Or not empty space. It contains 7. It's mostly empty space, but it contains 7. So the complement of the union in this case is just 7. This is going to be called A or B complement. And you might read this as neither A nor B. Okay, so now for the new information. So what we're going to talk about today is called the conditional probability. So up until now we've been considering events without considering their sequence, right? So there's non-sequential events. So we've just been kind of doing A or B, A and B, neither B nor A. And we haven't actually thought about, like, what order they come in or anything like that. But in real life, you're going to get this sort of situation. Okay, so let's consider sequential events. Let's see how this looks. So this first example says, suppose we want to know the probability of selecting 2 red cards from a deck of 52 playing cards without replacement. That is, we draw the first red card and don't put it back into the deck. And then we draw a second card. Okay, so in general, the probability of A and B, we know this to be written like this, but here's the actual formula for it. It's probability of A times the probability of B given A. Okay, so this little line here denotes given. So this is our first event, probability of A, and here we have probability of B given A. Okay, so this is the formula we're going to use when we have dependent events. So let's see how this looks. So I'm interested in drawing 2 red cards without replacement. Without replacement. So first we're going to calculate the probability of selecting a red card, and then we're going to calculate the probability of selecting a red card given that the first card was red. Okay, so in general we have a deck of 52 cards. We know half of them to be red, so that's 26 out of 52. Now, if we're considering this event as already happened, right, you've taken 1 red card out of your deck, well, now you only have, instead of 26 red cards, you only have 25 red cards left. And instead of a deck of 52 total cards, you have a deck of 51 total cards. Okay, so if we were to select red cards, a second red card, there's only 25 left out of 51 total. So the first one reduces to 1/2. So this probability comes out to 25 over 102, approximately 24.5%. All right. Now let's consider the scenario that we actually had put that red card back. So we have the same scenario. We want to select 2 red cards, this time with replacement. So we draw the first card, we put it back into the deck, shuffle it, and then draw a new card at random. So how would we go about calculating this? This time we have the probability of A and B. The formula is equal to the probability of A times the probability of B given A. But this time, B is independent of A. Because we put the card back, it's as if A never happened. That means our formula just becomes the probability of A times the probability of B. Okay, for independent events, B given A is just equal to the probability of B. Okay, so we don't need to actually consider that A happening anymore. So this is the case for independent events. So let's see how this calculation looks. The probability of drawing 2 red cards with replacement. This is going to be equal to simply the probability of drawing red times the probability of drawing red again, without consideration of that first event. It's almost as if it never happened. So this probability is still 26 out of 52, and for the second time it remains 26 out of 52. Nothing changes. These both simplify to 1/2, and your total probability comes out to 1/4, or 25%. Okay, so let's consider one more example involving conditional probability. So this is find the probability of selecting a red card and then a black card, and this is the case without replacement. Okay, so the probability of A and B is equal to the probability of A times the probability of B given A. In this case, we are going to need to use B given A. This is without replacement, so that second probability is going to be affected by the first. Probability of picking red and black is equal to the probability of picking a red card times the probability of picking black given that red was already picked. So as we know, for the first one it's going to be 26 out of 52. Now, for the second one, we know the case where when it's without replacement, the total number of cards in the deck have decreased by 1. Right? So now we have only 51 cards instead of 52. However, we still have 26 black cards. Okay, so if the first card we picked was a red, it's coming out of the 26 red. Right? So now there's 25 red, but there still remain 26 black cards. So this reduces and we'll have 13 out of 51, which is approximately 25.5%. Okay. So to review, the probability of A and B for dependent events is given by this formula. Probability of A and B is equal to probability of A times probability of B given A. Now what we can do, let's say we're interested in knowing just the conditional probability. Right? What's the probability that something happens given that something else has already happened? Well, what we can do is we can rearrange this formula and isolate probability of B given A. Okay, so this involves a little bit of algebra, but it's very simple. All we're doing is dividing both sides by probability of A. So probability of B given A is equal to the probability of A and B divided by the probability of A. So this gives us the formula for conditional probability. And this applies the other way too. Suppose A and B happen in opposite orders, right? Or in the reverse order. You can calculate the probability of A given B. And this formula comes out to the probability of A and B divided by the probability of B. Okay, so these are both conditional probability formulas. So let's look at an example of how we can use this. So it's the same table from last time, which compares education and marital status for 665 people. So in the first example, we have to calculate the probability that someone is single given that they have less than a high school education. Okay. So first we're going to consider the probability that they are both single and have less than a high school education. And then we're going to divide that by the probability of the prior condition. So the probability that they have less than a high school education. Okay. So the people that meet both criteria are going to be these 17. So it's 17 out of 665. And it's going to be divided by the probability that someone has less than a high school education. So it's 125 people total out of 665. Now when you're dividing fractions, it's the same thing as multiplying by the reciprocal of the denominator. So this entire thing comes out to 17 over 125. Now another way you can think about this, right, so you should always keep this formula in mind, but sort of a quick way to check is, well, we're considering the people who are both single and have less than a high school education, that's 17 people, and it's sort of out of all of the people, right, because we already know they have less than a high school education. There's only 125 people total who are like that. So that's why it's sort of like 17 out of this 125. All right. The next example is the probability that someone is divorced given that they went to college. So on top, we've got the probability that a person is divorced and went to college. On the bottom, we've got the probability that someone has gone to college. Okay, so let's find our new values. The probability that someone is divorced and has gone to college. Well, we've got 15 out of 665 people total, divided by the probability that someone went to college, which is 143 people out of 665. And this is going to reduce to 15 out of 143. Okay, and finally, so now we're going to consider the reverse probability, or the reverse conditional probability. Probability that they went to college given that they're divorced. So the numerator is the same. It's still the probability that someone is divorced and went to college. But now, the prior condition is their marital status, that they are divorced, rather than their educational status. Okay, so on top it's still 15 out of 665, but on the bottom, it's now going to be 84. Or 84 out of 665. And this comes out to 15 over 84. Right? So out of those 84 people who are divorced, 15 of them also went to college. And these are our conditional probability calculations. Now, last time we were in person, I asked some of you, right? So we were talking about flipping coins and coming up with sort of the probabilities, right, of certain sequences. And I asked, which sequence do you think is more likely? Right, so we have the first one, heads, tails, tails. And the second one is heads 5 times in a row. Now, a lot of people instinctively said, well, the first one's the more likely one, right? You've got some mix of heads and tails. It's a lot more realistic than just getting all heads. But now that we have this concept of dependence and independence, we have to think, right? Is the probability of every successive flip, is that affected by prior flips, right? Does the coin have some sort of memory, right, or conditioning from the prior events? And the truth is it doesn't, right? A coin has no concept or memory of prior results. Unlike a deck of cards, it's not affected by previous selection, right? So a deck of cards, if you're not replacing it, sure, right, you're going to reduce the total amount of cards, you're going to reduce maybe the number of black cards or red cards that you have. That's not the case for a coin, right? It remains unchanged. Therefore, coin toss results are independent events. Now, what we know, right, the probability of independent events is going to be the probability of A times B. Now, this was just 2 events. But this sort of arrangement, or this fact, kind of holds no matter how many events you have. So as long as they're independent, you can keep just sort of multiplying the probabilities. Right? So say you had events A through Z, you would just be multiplying the probability of A, probability of B, probability of C, all the way down to probability of Z. So it's still just a product. So if we're going to do this for our 2 events, right, we'd have to do probability of heads, 1/2, times probability of tails, 1/2, 1/2, and 1/2. 5 times in a row. And this would come out to 1/32. And you would do the same thing here. 1/2, 1/2, 1/2, 1/2, and 1/2. And this also comes out to 1/32. So now, given our new formula, right, of independent events, what we see is that both sequences are actually equally likely, right? And this is just the case because any specific sequence of events that we specify, it's going to be equally likely with coin tosses. So it's not that we were considering any mix of heads and tails, right? We're considering this specific mix of heads and tails in this specific order, right? Only 2 heads and 3 tails showing up in exactly this sequence. That's just as unlikely, it turns out, as getting all heads or all tails or any other specific sequence of events. Now, an important way this kind of shows up in real life is what's called the gambler's fallacy. So this is the incorrect belief that if a particular outcome has already occurred more frequently than expected, then it's now less likely to occur in the future. And this is the case for independent events. So, you wouldn't expect 5 heads in a row, or right, maybe 16 heads in a row or something like that, because we expect, well, it's equally likely as heads to show up as tails, right? But so intuitively you might think this is an unlikely result, and you're going to think, well, it's more likely for tails now to show up on the next flip, or much more likely the more heads we have in a row. But this is in fact a fallacy. This is gambler's fallacy. Okay, so a famous sort of instance of when this happened was at the Monte Carlo Casino in 1913. So during a game of roulette, this is where one bets, they throw a ball and it lands on either red or black, and you bet what color it's going to land on. The ball had fallen on black 12 times in a row. Now, a lot of people there thought, well, this is just too unlikely to happen. And it's too unlikely for the ball to fall on black again. And it turned out, so they, in sum between all of them, they bet millions of francs, which was their currency in Monaco, on red showing up. Well, it turned out the ball proceeded to land on black 14 more times. Okay, and they lost millions thinking that, some sort of big red streak was going to occur, or that the outcomes had to balance out somehow. It didn't work out that way. Okay, so while this is an extremely unlikely occurrence, it is a real-life example that independent events are completely unaffected by previous outcomes. Assuming that this game wasn't biased or rigged. It's extremely unlikely, but just like you saw with the coins, it's as extremely unlikely as any specific sequence of events. Right? So that doesn't make it impossible in any way whatsoever. All right. That's all for probability part 3.